Alright, let's talk about circular orbits when a particle is moving under a central force governed by a specific type of potential energy. So here's the question we're looking at. We have a particle with mass m that's in a stable circular orbit at a specific radius, let's call it r0. It also has a given angular momentum L. The potential energy governing its motion is V of r, which is equal to beta times r to the power of k. We are told that beta is greater than 0 and k is greater than 0. Given this setup, we need to figure out which of the following options is the correct one describing this orbit's radius r0. We have four options presented, each giving a value for k and a corresponding formula for r0 involving Lm and beta. Our goal is to determine which of these is correct. Let's dive into the solution by thinking about the effective potential energy. We are given that the particle is moving in a central potential V of r, which is beta r to the k, and it has angular momentum L. When dealing with motion in a central force field, it's often helpful to use the concept of the effective potential energy. The effective potential V effective of r combines the actual potential energy V of r with a term related to the angular momentum. The formula for the effective potential is V effective of r equals V of r plus L squared over 2mr squared. Now we just substitute the specific potential energy we were given, V of r equals beta r to the power of k. So our effective potential energy becomes V effective of r equals beta r to the k plus L squared over 2mr squared. For a particle to be in a circular orbit at a specific radius r0, the effective force acting on the particle must be 0. Since force is the negative derivative of potential energy, this means the derivative of the effective potential with respect to r must be 0 when evaluated at r equals r0. You can see this condition written mathematically on the slide. Next, we calculate this derivative using the V effective formula shown previously. Taking the derivative with respect to r gives us the expression shown here. Simplifying the second term leads to the final form. Okay, so to find the radius of a circular orbit, r0, we use the condition that the derivative is 0 at this specific radius. First, we rearrange the equation that comes from setting that derivative to 0. Next, we group all the terms involving r0 together on one side. We then isolate the r0 term. And finally, to solve for r0 itself, we raise both sides to the power of 1 over k plus 2. This gives us the general formula for the radius of a circular orbit for this potential. Now that we have our general expression for r0, we can compare it with the options given in the question. Let's check option 1. It provides specific values for k and r0. Substituting the given k value into our derived formula, we get an expression for r0. Comparing this result with the r0 given in option 1, we see they do not match. Now let's check option 2. It gives k equals 2 and another expression for r0. Substituting k equals 2 into our derived formula, we get a new expression for r0. Comparing this result with the r0 given in option 2, we find they match exactly. Let's continue comparing just to be sure. Option 3 says k equals 2 and r0 is the quantity L squared over 4m beta, all to the power of 1/4. Our formula for k equals 2 gave r0 equals the quantity L squared over 2m beta, all to the power of 1/4. This does not match option 3. The denominator inside is different, 2m beta versus 4m beta. Option 4 says k equals 3 and r0 is the quantity 5l squared over 3m beta, all to the power of 1/5. Our formula for k equals 3 gave r0 equals the quantity L squared over 3m beta, all to the power of 1/5. This does not match option 4. The numerator inside is different, L squared versus 5l squared. Based purely on finding the radius of the circular orbit by setting the effective force to 0, option 2 is the only one that matches our derived formula for the specified value of k. The question also specifies that the orbit is stable, which is a good check. For a circular orbit to be stable, the effective potential must have a minimum at the orbital radius r0. This means the second derivative of the effective potential with respect to r must be positive when evaluated at r0. So, the condition for stability is that the second derivative evaluated at r0 must be greater than 0. Let's calculate the second derivative. We take the derivative of the first derivative we found earlier. The result of this differentiation is shown here. Now we evaluate this second derivative at r equals r0 and require it to be greater than 0, leading to the inequality you see. We are given that beta, k, m and l are all positive, and r0 being a radius is also positive. Looking at the second term in the inequality, since all its components are positive, this term is always positive. For the entire sum to be greater than 0, the first term must be non-negative. Given that beta is positive and r0 to any power is positive, This requires that k times k minus 1 must be greater than or equal to 0. Since k is positive, this simplifies to k minus 1 being greater than or equal to 0, meaning k must be greater than or equal to 1. Option 2 has k equal to 2. Since 2 is greater than or equal to 1, the condition for stability is satisfied for option 2. The orbit described is indeed stable. So to wrap up, we derived the general formula for the radius of a circular orbit in this potential R0 equals the quantity L squared over mk beta, all raised to the power of 1 over k plus 2. Comparing this general formula with the given options, we found that option 2 matches our result exactly when k equals 2. For k equals 2, our formula gives R0 equals the quantity L squared over m times 2 times beta, all raised to the power of 1 over 2 plus 2, which simplifies to the quantity L squared over 2m beta, all raised to the power of 1/4. This is exactly what option 2 stated. Therefore, the correct option is 2.